sandwich 1 or sandwich 0. Now, the sandwiches in this case are 0, 1, 0, and 1 again. The order of this matters because we have is more simple than they make it out to be. So I'm going to ignore a lot of the context of this problem. Let's say we have one array students. And so this is just the preference of every single student. So one student prefers 1, another student prefers 1, then the other 2 students prefer 0. And the order of this matters in theory, at least the way they describe it in this problem, but I think that's just to confuse you. So they tell us that this is the student at the beginning of the queue, like the beginning of the lunch line, and this is the student at the end of the lunch line. And they also tell us that we have a second array called sandwiches, and this is the order that the sandwiches have to be served. And so the preference, by the way, here is like the sandwich. So this is sandwich 1 or sandwich 0. Now, the sandwiches in this case are 0, 1, 0, and 1 again. The order of this matters because we have to serve sandwich 0, and then we have to serve sandwich 1, and then we have to do this one and then this one. So they ask us, well, first of all, the length of these two arrays is always going to be equal. Now they ask us, how many students are we able to serve? And the rule, the way they describe it in the problem, is this. If this student matches the preference of the first sandwich, then they can take it. If they don't match the preference, then we move this student to the end of the queue and then ask the same question for the next student. And this student also doesn't like it. So, okay, we move them to the end as well. Now we have this student who does like this sandwich. Great. We've served 1 sandwich. So we kind of repeat this process. Here we see that this student doesn't like this sandwich, so they go to the end, and then we would kind of repeat the process. Now doing this simulation might be possible, but it's kind of annoying. And the ultimate question that we're trying to answer here is how many sandwiches are going to be left remaining, which is equivalent to saying how many students are not going to eat a sandwich. Because remember, the length of this is going to initially be the same as the length of this. So if we have 2 students who never ate a sandwich, then we'll probably have 2 sandwiches remaining. Now, in this example, this student will get this student will get this student will get this, and then this student will get this. So it works out. We have exactly 0 sandwiches remaining, 0 students did not eat lunch. So what possible case would allow us to have some sandwiches left over or have some students who did not eat lunch? Well, let's change this example slightly. Let's say this is now going to be a 1. Let's see what happens. Okay, this student gets this sandwich, great. This student gets this sandwich, great. This student gets this sandwich, that's also great. Now, this student has a preference of 0, but we don't have any zeros left over. There's a 1 here. So basically, the only time we're going to have some sandwiches left over or some students left over is when there is a mismatch between them. So this has to happen for us to not serve sandwiches. Because notice, when they tell us in the context of this problem that a student will be then at the end of the queue, what they're essentially saying is that the order of the students doesn't really matter. We don't have to serve the students in this order. We can skip this student and then serve this one and then come back to this student later. So the order of this does not matter at all, but the order of the sandwiches does matter. They have to be served strictly in this order. So the order of this matters slightly more, but only to the point where we get to a sandwich and we just do not have any students that are willing to eat that sandwich. That's what matters here. So let me just show you a couple more examples to make this 100% clear, and then we're going to go ahead and code this up. So I'm going to change both of these to 1s. So we have 4 students who want sandwiches of 1. Now suppose this is the order of the sandwiches. I start with a 0 here. None of the students are willing to eat that sandwich. Therefore, the result of this would be 4. We have 4 sandwiches left over. We have 4 students who did not eat a sandwich. Now, suppose I change the order of these. Suppose I change it to this. 1, 1, 1, now 0. Now I have 3 students who got a sandwich, and then we got to 0 and nobody was willing to eat a 0, or this student wasn't willing to eat a 0. So therefore we would return 1. That's what I mean by the order of the sandwiches matters a little bit, but ultimately what matters about the sandwiches is the quantity of each of the sandwiches as well. The way I'm going to solve this problem is by initially counting the students. I'm going to create a hash map, or just, we wouldn't really need a hash map. I'm just doing this for convenience. You could just have 2 variables, but basically I want to know how many students are going to eat the sandwich of type 1. And initially we have 4. How many students are going to eat the sandwich of type 0? Initially we have 0. With this count, we're going to go through every sandwich. We see, okay, we need a student of type 1. We have a student of type 1, so therefore we decrement the count to 3 now, and we eat this sandwich. We do that for every single one of these sandwiches until the count, I guess, of this is going to be down to 1. And then we get to 0, and we see nobody is willing to eat a 0 because the count of 0 is equal to 0. Nobody is willing to eat that. So this is how we can solve this problem pretty efficiently. We can do it in a single pass. That's going to be big O of n, and we do have to count the occurrences of each value here, which is also O of n, at least time. The space complexity, even though we have a hash map, is going to be constant, because notice how we only have 2 keys for the hash map. We're going to count the number of 1s and we're going to count the number of 0s. So now I'm going to go ahead and code it up. So I'm going to initialize the result to either the length of sandwiches or the length of students. Doesn't really matter. And we're going to assume that these are the students remaining. These are the students so far that have not eaten lunch, and then eventually we're going to decrement it, and then we're going to return that result. So now for how we're going to do this. First things first, I want to count the occurrences of the students, what their preferences are. We could do that manually. We could do that like this for S in students, for every single student, and then create a hash map up above. Let's call it count, and then increment for every single key in this hash map. An easier way to do that in Python is basically, let me just write out the code. Like first we'll check if S is in count, and if it is, then we'll just, well, I guess first we could check if S is not in count, and then we will insert it. So we'll map that student to a count of 0, and then here we would do something like this, just incrementing it by 1 each time. An easier way to do this in Python is to use something called a counter, which is basically going to do exactly what I just showed you. So passing in the students array, it will count the occurrences of every single integer in this array, put it into a hash map. Now that we have that, we're going to go through every sandwich, and we do have to go through this in order. We do have to go through from left to right. So for every sandwich in sandwiches, let's check if the count of this sandwich. So for this sandwich, we're saying, do we have any students willing to eat that sandwich? Is the count greater than 0? If it is, then we just fed that student. And if we're doing that, let's decrement the result by 1, and let's decrement the count of that by 1, because maybe we had 4 students initially willing to eat this sandwich. Now we only have 3, so that's why we're decrementing this by 1. Now, if this is not true, what does that mean? That means we don't have any students through every sandwich, and we do have to go through this in order. We do have to go through from left to right. So for every sandwich in sandwiches, let's check if the count of this sandwich. So for this sandwich, we're saying, do we have any students willing to eat that sandwich? Is the count greater than 0? If it is, then we just fed that student. And if we're doing greater than in sandwiches, let's check if the count of this sandwich. So for this sandwich, we're saying, do we have any students willing to eat that sandwich? Is the count greater than 0? If it is, then we just fed that student. And if we're doing that, let's decrement the result by 1, and let's decrement the count of that by 1, because maybe we had 4 students initially willing to eat this sandwich. Now we only have 3, so that's why we're decrementing this by 1. Now, if this is not true, what does that mean? That means we don't have any students willing to eat this sandwich. Therefore, we have to terminate. We have to return our result immediately. So this is the entire code. Let's go ahead and run it to make sure that it works. And as you can see on the left, it does. It's pretty efficient. If you're preparing for coding interviews, check out neetcode.io. Thank Thanks for watching, and I'll see you soon. Hey everyone, welcome back, and let's write some more neat code today. So today let's solve the problem, time needed to buy tickets. So the premise of this problem is similar to the last one. We still have kind of a queue of people. In this case, though, we're given two inputs. We're given an array called tickets. Now, this actually represents the number of tickets each person wants. So the first person in the queue wants to buy 2 tickets. The second person in the queue wants to buy 3, and then the last one wants to. We could model it that way if we wanted. Just have a pointer, right? So this pointer will now be over here. Next person wants 3 tickets, but they can only buy a single one, so they buy 2. Now we're over here. This person wants to buy a ticket, they can only buy 1, so now this is what our queue looks like. Everybody still needs to buy at least 1 more ticket. Now next, this person could buy their last ticket. Now they only want 0 tickets. Now we're here. This person buys a ticket, only 1 ticket. This person buys 1, 0 tickets left. So now it kind of becomes useless to have a pointer because not every pointer is going to be at a valid value. This person wants 0 tickets. We can skip them now. We can automatically go over here. This person wants to buy a ticket, so they buy it, and now we're left with all zeros. Nobody needs any more tickets. So that's how we could run the simulation if we wanted to with an array. And again, you could also more appropriately run the simulation if you are using a built-in queue data structure, because you could pop from here and then push here, pop here, push here, etc., etc. If we ever got to a 0, then we pop it, and then we have no need to push it to the end of the queue. The person doesn't need any more tickets. So that's why it's kind of a queue problem. But and so the queue is ordered in this way. The problem is that a person can't buy 2 tickets. They can only buy 1 ticket at a time. So this person buys a ticket. Now they only want 1 ticket. Okay, now this is the beginning. of the queue. So in a sense, this person goes to the end of the queue, and we could model it that way if we wanted to. We could use a built-in queue data structure. That's perfectly valid, but the problem is easier than that if you can recognize a couple things. And I'll try to explain the intuition of how we can make those observations that will make us be able to solve this problem more easily. So for now, let's just say, okay, this person bought one ticket, now they only want one. We can, instead of manipulating this like a queue, we can just have a pointer, right? So this pointer will now be over here. Next person wants 3 tickets, but they can only buy a single one, so they buy 2. Now, we're over here. This person wants to buy a ticket. They can only buy 1. So now this is what our queue looks like. Everybody still needs to buy at least 1 more ticket. Now next, this person could buy their last ticket. Now they only want 0 tickets. Now we're here. This person buys a ticket, only 1 ticket. This person buys 1, 0 tickets left. So now it kind of becomes useless to have a pointer because not every pointer is going to be at a valid value. This person wants 0 tickets. We can skip them now. We can automatically go over here. This person wants to buy a ticket, so they buy it, and now we're left with all zeros. Nobody needs any more tickets. So that's how we could run the simulation if we wanted to with an array. And again, you could also more appropriately run the simulation if you are using a built-in queue data structure, because you could pop from here and then push here, pop here, push here, etc., etc. If we ever got to a 0, then we pop it, and then we have no need to push it to the end of the queue. The person doesn't need any more tickets. So that's why it's kind of a queue problem. But this is the observation that we can make that will make the problem pretty trivial. First, I guess we should start with what exactly are we trying to figure out? Like, we're not trying to run the simulation, we're trying to actually answer a specific question, and that question comes from the second input parameter. So that parameter in this case is k equals 2. What that means is the person at index 2, which is this, because we're 0 indexed, this is 0, this is 1, this is index 2. We want to know how many turns does this person have to wait to buy their tickets. Now, that's not how they really phrase it. They say 1 second, so I guess I'll stick with that. So every time we want to buy a ticket, it takes 1 second. So this person to buy a ticket, now they only want 1 ticket, that took a second. Now this person wants 2 tickets left. Now 2 seconds have passed. This person wants to buy a ticket. Now they only want to buy 1 ticket. So doing those 3 turns, those 3 steps took 3 seconds. And if we continue again, this person buys a ticket, 0. This person buys 1, 1. This person buys a ticket, now 0. So in total, it took 6 seconds before the person at index 2 bought all the tickets that they wanted. That's the question we're trying to answer. How many seconds does it take before this person buys all the tickets that they want? And if our parameter k was equal to index 1, then we'd be asking how many seconds before this person buys all the tickets that they want. It would take 1 additional second, because now they get to buy a ticket, so then it would take 7 seconds. So at first, it seems like you have to run the simulation to answer the question, right? But there's a pattern here. Let me kind of explain it to you. It took 6 seconds for this person to buy both their tickets. Why is that? Let's dissect it. First of all, for this person to buy their tickets, the people ahead of them have to make a move. So this person wants 2 tickets. Therefore, everybody before them has to go twice, like through that line of buying tickets. This person would have to go twice, this person would have to go twice, and then this person would have to buy both of their tickets. After these people have gone twice, it would take 6 seconds. But is that always going to be the case? Consider this. What if the value here was actually a 1? This person only needs to go and buy a single ticket. Well, they're going to buy that ticket in 1 second, and then they're never going to buy another ticket. So then they wouldn't need any more tickets. This person, though, would still have to go ahead of this person twice. So it would take 1 second for this person, it would take 2 seconds for this person to go twice, and then this person would buy both of the tickets that they want. That takes 5 seconds. What's the pattern? What's the difference between this new example I showed you and the previous example we were looking at? Pretty much this. We go to index k, this is the person we care about. Then we go through every person before this person, and we add to our total, which I'm going to call the result. So this is the number of seconds we're trying to total up, and we're going to go through every value, and we're going to ask a simple question. is this value less than the value at index k? If it's less than the value at index k, we take this value itself and add it to the result. It's just 1. We go to the next value. Is this value less than the value over here? It's not. So what do? It's 3. But does this person really have to buy 3 tickets before this person can buy 2 tickets? Nope, they definitely don't. What we're recognizing here is that the person at index k is the bottleneck. So either we will take a value here which is smaller than 2 and add that to the result, or this value is greater than 2, in which case we're just going to still add 2 because we only need this person to go twice before this person can buy a ticket. And to finish the example, we get to the person at k and add their value, which is 2. So in this case, it would take 5 total seconds. Now let's quickly go back to the previous example where this was a 2, just to spot the edge case, where this value is equal to the value at index k. In that case, we also would add that value. So basically, if this is less than or equal to the value at k, we add that to the result. And if it's greater, we will just add the value at index k to the result. And for this value itself, we'll add that as well. So in this case, we would get 6. There's one last thing that this first example doesn't actually illustrate for us, because it's a special case where the index that we're considering only has people in front of them. What about if there were people behind this person? That matters as well. So let's change this example to k equals 1. Now we want to know how many seconds does this person have to wait before they get to buy all 3 tickets. So let's follow what we had before to our result. We're going to go through every value. We're going to see this one, it's less than or equal to this. So we're just going to go ahead and add 2. This person definitely needs to buy 2 tickets before this person can buy 3 tickets. Okay, now we get here. This value is 3. It's less than or equal to 3 technically, so it does follow our rule. So 3 is going to be added. That makes sense because this person, of course, needs to go 3 times before they can buy all 3 tickets. Now, though, when we get behind, in this case, it is true that this person needs to buy 2 tickets before this person can then buy their 3rd ticket. So technically, we do add this value to the result. But is that always going to be the case? Let's change the example for a second. What if this was a 3? Does this person need to buy 3 tickets before this person can buy their 3rd ticket? I mean, this person is ahead of this person. So really what's true is this person only needs to buy 3 minus 1 tickets before this person gets the 3rd turn. So for any value that's going to come after index k, if that value is less than the value at index k, which it was previously when this was a 2, we will go ahead and take that value and add it. But if that value is greater than or equal to this value, then we can ignore that value and just replace it with this value minus 1. So 3 minus 1, which is a 2. So in that case, we would add 2 here, and it would only take 7 seconds for this person to buy all the tickets that they want. Just to make this even more crystal clear, let's replace this value with a 10. This person wants to buy 10 tickets. So are we going to add 10 to this? No, of course not. We don't need this person to wait 10 seconds before they buy their 3rd ticket. We only need this person to buy 2 tickets before this person can buy their 3rd. So again, we would replace this value with the value that goes here, minus 1. So we'd put a 2 over here. So it's all about how we add values that come before index k and add values that come after index k. So knowing that, I'm going to go ahead and code it up. This is a linear time algorithm, by the way, because we're just iterating once. We're not doing like the entire simulation, and it's constant space because we don't really have any data structures. We're just keeping track of what the result is. Okay, so I'm going to initialize the result to 0. This is like the number of seconds that it's going to take for the person at this index to buy all the tickets that they want. And this is what we're going to end up returning. So now I'm going to iterate over every position in the input length of tickets. And I am keeping track of this index because we know it kind of does matter, because we know there's 2 cases. Either I is greater than or equal to index k, and the reason I'm saying equal is because the value at index k matters as well, or it's not. And the else case is that the index I Well, I guess actually this should be the opposite. We want this to represent where the index has not passed k, and this is going to represent when the index has passed k. So what we learned is everybody before and equal to k has to buy tickets before this person. And either the value, so let's say nums of I, is either equal to k or it is less than k. So basically what we're saying is we want to take the minimum of these two values. We could write an if statement if we wanted to, but the easier way to code this up is to take the minimum. So either this value is less than this value, or this value is greater, in which case we want to replace it with this value. So what we're saying is we want the minimum of these two. That can be taken pretty easily. This is basically the number of times that this person would have to buy a ticket before this person can buy all the tickets that they want to. So this is what we add to the result. And I realize I'm using nums here when we should be using tickets. Sorry about that. Now, the else case is going to be pretty similar. The only thing was that the person at index I does not need to buy this many tickets, doesn't need to buy the same number of tickets as the person at index k. So they only need to buy at most this many minus 1 tickets. So either this value is less than this value, which is fine, or it's equal to this value or greater than this value, in which case we want to replace this one with this minus 1, just like we kind of did in the drawing explanation. I know this is a little bit different than how we kind of talked about it in the drawing explanation, but the core principle is kind of the same. The only difference is I'm using the min function here when we could just be using an if statement. Like we could have been checking, is this less than or equal to this, and could have done the same thing like up above, but to be more concise, leaving it like this. So this is the entire code. Let's go ahead and run it to make sure that it works. And as you can see on the left, yes, it does. If you're preparing for coding interviews, check out neatcode.io. Thanks for watching. Is this less than or equal to this? and could have done the same thing like up above, but to be more concise, leaving it like this. So this is the entire code. Let's go ahead and run it to make sure that it works. And as you can see on the left, yes, it does. If you're preparing this minus, the only difference is I'm using the but to be more concise, leaving it like this. So this is the entire code. Let's go ahead and run it to make sure that it works. And as you can see on the left, yes, it does. If you're preparing for coding interviews, check out neatcode.io. Thanks.
will return our int option. See this arrow? This arrow represents a pointer to the next element in the list. At the end of the list, you do have a third pointer here, but this pointer points out to null, which determines that we are at the end.
Hi, I'm Gail Locke McDowell. Element right to the beginning of the linked list, that can be done in constant time. If you want to delete an element from the beginning of the linked list, again, constant time. So that's very, very fast. Of course, if you want to append an element to the end of the linked list, that might require walking all the way through the linked list until you get to the very last element, and then inserting the element there. That will take linear time. So it all depends really on what you're looking for. Now there's one other thing we should talk about before we dive into the code, and that is this alternate version called a doubly linked list. A doubly linked list is just like a singly linked list, but in addition to each element having a link to the next element, each element also links to the previous element. For certain operations, that can be quite handy. Now that we've covered the basics of a linked list, let's take a look at what the code would look like. Implementing a linked list is reasonably straightforward. We just need a class node that has a next value and a data. And then just to make our lives easier, we'll add in a constructor and set that value. Okay, so the first method we'll want to implement is an append method. So let's go ahead and get started with that. Append is going to take in a data value, and then it's going to have some pointer that starts off with at the current node, so the head of the linked list. And then it's going to walk through the linked list until we get to the end of the linked list. Well, how do we know that we're not at the end of the linked list? Well, we're not at the end of the linked list as long as there's something after it. So in other words, while current.next does not equal null, keep moving, get to the end of the linked list. Then, when we get down to the end of the linked list, create this new node. If we prepend an element, we're going to actually change what the head node is. Now this makes a little bit of an issue because we could have multiple places in our code base that all link to the same head. But if we change the head in one place, how does everybody else know that our head value changed? So the workaround for this is rather than giving everybody an access to the head pointer directly, we define a class linked list that's basically going to wrap our head. And then this append method can go where it probably should have from the beginning, which is in this linked list class. And let's just update this because the current node should actually point to the head. And what's nice here is that we can also add in the case if the head is null. So we can say if the head is null, then actually we just want to create the head. So if head is null, head equals new node data, and then we can just return because now we're done with that. All right. Prepending is relatively easy now. We just need to, so it's going to be void again, prepend taken data. Now, the way this method will work is that we're going to create actually a new head value. So node new head equals new node data. Then new head's next value is going to link over to the old head. And then we need to change the head pointer. For our final operation, let's implement a method delete that deletes the first node that has a particular value. So first we'll just declare our method void delete with value that takes in a piece of data. Okay. Now, if head is null, we know we just want to return immediately. There's nothing we can do there. Now, what delete with value is going to do is it's going to walk through the linked list, and it's going to stop one before the element we want to delete. And then it's going to say, uh-oh, the very next element you want to delete. So I'm going to actually just update my pointers to work around it. So my next pointer is going to be that deleted value's next pointer. So let's see how this works. So first we'll have this little current method that walks through the linked list. And then we're going to walk through as long as we're not at the last element, so we don't want to run off the edge of the linked list. Okay, now if current.next.data equals the data we're trying to delete, so in other words, if the next value is the one you want to delete, then cut out that next value. So then current.next equals current.next and next. And then we return. So what this is doing is saying, okay, if the next value you want to delete, don't go to that element and just walk around it. Set my next pointer to be my next pointer's next pointer. So walk around it. And then in other cases, we just move on to the next element. Now there's one case we want to be very careful of here, which is what happens if the node we want to delete is actually the head node. This will actually cause a problem in our current scenario because we need to actually update the head value. So we can just special case that. If head.data is the data we want to delete, then head equals head.next. That is, just cut me out of the linked list. So now let's take a look at what our method does. So first it takes in this data and then says, okay, if head is null, return. There's nothing we can do. If we need to delete the head, then just go and delete it. Set head equal to head.next, set equal to the next value. Otherwise, walk through the linked list starting at the head value. Then, as long as, walk up until the next value is the one we want to delete, in which case we say, okay, set current.next, my next pointer, over to the next value, and then we return. Otherwise, we continue walking through the linked list. So those are the basic operations for deleting, inserting, both appending and prepending into a linked list. Now that you've seen the basic operations, why don't you give it a shot on a new linked list problem? Hi, I'm Gail Locke McDowell, author of Cracking the Coding Interview. Hi, I'm Gail Locke McDowell because breadth first search is designed for finding the shortest path. So it's perfect for that problem. Now remember in breadth first search that we're going to need to have some sort of queue that
this lesson, we are going to see the difference between tu, te, and toi in French, and why there is a difficulty. Well, there is difficulty because these three words are just one in English. You. And we are going to see so the difference between these three words. First, when you is the subject of your sentence, so you followed with a verb. In this case, in French, we use the subject tu. You love French language, for example. So here you is before the verb, so it's a subject in French. It is tu aimes le français, or t'aimes le français when we speak fluently. Do you love French? A question, so the same thing. Aimes-tu le français? So the subject is tu in French. However, when we want to emphasize on the subject, we use toi. For example, toi, tu aimes le français. So you do like, you do love French. Or, also to translate, and you or what about you? J'aime le français. Et toi? Let's see now. After a preposition, the French word is toi. For example, if you say for you, so the preposition is for, so in French it is pour toi, and here we translate you in toi. With you, avec toi, without you, sans toi. Of you, de toi, etc., etc. We also use toi to translate the expression yourself. We say toi même. We use toi imperative mood, but with reflexive verbs. So the imperative mood to give order or invitations. With reflexive verb, for example, to say get up, we say lève-toi. Or to say sit down, we say assieds-toi. Let's see now the third part. Verb, and this time you is after the verb. It's not the subject, the object. And we use te or t apostrophe in French. I love you. So you is not the subject here, it's the object. And in French it is je t'aime, t apostrophe, because of the vowel. He knows you. Again, the subject is he, so the object is you. Il te connaît. As you can see, we put te before the verb and not after. She looks at you. Here, actually, there is difficulty because in English we have a preposition at, but in French there is no preposition. The verb is regarder. So we use te. Elle te regarde. With reflexive verbs, we also use the expression te or tu apostrophe. Tu te laves, you wash yourself. And to emphasize, again, we are going to use toi. Il te connaît, toi. Here you want to emphasize about you. So if we want now to summarize, you and the verb we say tu, verb and you we say te or t apostrophe, and after a preposition, but in French of course, it is toi. And toi also to emphasize. Ok? Allez, c'est fini. Alors au revoir et bon français.
Bonjour, in this video we are going to look at the difference between tu and about toi. Toi, as we know, is an emphatic or stressed pronoun. It is not a subject pronoun. Toi, therefore, is never found in front of a verb. You wouldn't say, like the example I've mentioned before, tu joues au foot. We wouldn't say toi joues au foot. No. Toi can be placed at the end of a sentence. Toi can be used after certain prepositions. And let's have a look at a few, such as chez, when we talk about a person, place. So let's have a look at this example. Je viens chez toi à 19h. And you know that the emphatic comes after chez. I'm coming to yours at 7 p.m. Okay? Je viens chez toi. Of course, you could say je viens chez moi, but that's another emphatic pronoun. Okay? So another little words where I'm going to put these two together because they go well together is after the word avec ou sans. Okay, so avec with and sans without. You would put the emphatic pronoun after that. For example, il est parti sans toi. Or, il est parti avec toi. Okay? You would not say tu here because tu is a subject pronoun, okay? Not an emphatic pronoun. So, he's left without you or he's left with you. Another little word where toi comes afterwards or any emphatic pronouns would be à. Ce livre est à toi. This book is yours or it is at you. Technically, that's how we translate it, but it means it's yours, okay? So, ce livre est à toi. Ce livre est à moi. Ce livre est à nous. But you will never say ce livre est à tu, okay? Because we said tu is a subject pronoun. Thank you. You're following. Well done, you. Pour. That's another little word. Ce livre est pour toi. Okay, this book is for you. Of course, we have other little words like that, and there is more in your support guide. Now, toi can be used to form an imperative tense of a reflexive verb. And there, I've lost you all. Listen. Se regarder. It means to look at yourself, okay? Now, how would you transform se regarder, which is a reflexive verb, you know, that's where the yourself comes from, into an imperative verb? An imperative, I want to say, look at yourself. You know, that's an imperative. That is a order, okay? Or look, that's an order, and it's called an imperative in French. Well, when you want to create the imperative of a reflexive verb in French, you do it like that. If you wanted to say, look at yourself as in an order, you would use the emphatic toi and not tu. Okay, so regarde-toi. Okay, we wouldn't say regarde-tu. We would say regarde-toi. And I understand that regarde is a verb, but here toi comes after the verb and not before the verb. Tu regardes, you are looking, regarde-toi. Okay, look at yourself. So basically, we've transformed te, tu te regardes, you are looking at yourself, into toi in the imperative tense. Does that make sense to you? Now, toi emphasizes, you can't say that word, the identity of the person who is the star of the sentence. For example, you play football, right? So we would say, toi, tu joues au football, n'est-ce pas? Or we could say, tu joues au foot, toi, n'est-ce pas? Tu joues au foot, toi, n'est-ce pas? Okay? You see what's happening? We have placed toi as the main character, okay? But it's still not before a verb. It is after, or it emphasizes on that particular tu. Okay, so we say, toi, tu joues au football, n'est-ce pas? Or, tu joues au football, toi, n'est-ce pas? And we put a lot of moi and toi in French, okay? J'ai rien fait, moi. I've done nothing, me. That happens a lot in French. And last but not least, we use toi after the conjunction et, and. Never ever say tu after et, because I hear it so many times. You know what I hear? This. Comment ça va? Oh, ça va. Et tu? No, we wouldn't say and you like that. We would say et toi. Now, to go back to football, I don't like football. And you? Je n'aime pas le football. Et toi? Can you see what's happening here? Now, knowing what we know, let's now try to fill out the following sentences. I'm going to click my fingers and they are going to appear just like that. Ding! Okay, the exercise is quite simple. You see where the blanks are? I would like you to replace the blank by either tu, the subject pronoun, or toi, the emphatic pronoun. And I'm going to show you these sentences and give you like 10 seconds so we can work them out. You know, we've got 4 sentences, not hard. The first one is something mange tout le pain. Okay, what do you think here? Tu ou toi? That's right. Identify where the verb is. It's mange, okay? It is definitely tu, because we know that tu comes before the verb. Well done. So, tu manges tout le pain. You are eating the whole of the bread, okay? Tu manges tout le pain. Let's have a look at number 2. Je mange tout le pain. Et, okay. We know that. I know you're shouting at the screen. I know that. You're saying, mais toi. It is toi. Because I've literally just said that do not put tu after it. Okay, so I am eating the whole bread and you, okay, je mange tout le pain et toi. Do you know when I've written that? I must have been hungry because there is a lot of bread thing going on here. Now, numéro 3, and we've got 2 gaps here. Reste chez aujourd'hui. That's easy, isn't it? Okay, identify the verb, reste. What do we put before the verb? Tu. So, tu restes chez toi aujourd'hui. Well done. Tu restes chez toi aujourd'hui. We've put both pronouns here. And that's very clever, okay? Because you can see their role really distinctively. Tu, the subject pronoun, and toi, because it comes after chez, the preposition, okay? Tu restes chez toi aujourd'hui? Oh, tu restes chez toi aujourd'hui. You're staying at home today, at yours. Okay. And to finish, habille. Yeah, well, it's an imperative, isn't it, of a reflexive verb. So it has to be toi. Exactly. Habille-toi. That's an order. Bonjour, in this video in French.